I would like to welcome you to Lighthouse Engineering. Today we'll be doing part 3 of chapter 1 of our electrical engineering course. Now this part we will cover factors affecting resistance, and I will also be doing some examples, 2 examples actually, and I'll be giving you a tutorial at the end which hopefully you'll find really helpful because it's very examinable and it's quite common questions that you might be asking in your exam. So without further ado, let us begin. As I said from the last video, we'll pick up for where we left off, which we were starting with resistance and resistors. So first we will cover the factors that are affecting resistance. Okay. So our number one factor, that would be length. Now what about length? Now, depending on the length of the material that will be used, resistance of a material will be directly proportional to the length, meaning that the resistance of a longer wire has more length, will be required, will be using will be having more resistance, shall I say, and we will denote it by L. Okay, and our second factor, that will be the cross-sectional area. Now of course I am speaking about the wire, right? For example, if a wire is of circular cross-section and this is your area, let's draw it 2D more clearly. That would be the area where your electricity is running on, right? Now what's happening is that it will be opposite to the length, meaning that it will be inverse. This one is directly proportional, whilst this one will be inversely proportional. Okay, they are of opposite values. Meaning, what do I mean by inversely proportional? Well, if you have more cross-sectional area, then you will have a more number of electrons, hence offering less resistance. So if you have more area, the more the area you have, the more free electrons you would have, right? Which means it's a good thing to have a good cross-sectional area, and we would denote it by A. Well, in comparison to the length, which is the more length you have, the more the resistance. Here, the more cross-sectional area you have, the less the resistance, because you have more electrons running through it. Okay, now we go to our third factor that's affecting resistance, and that would be the type or nature of the material. Okay, now as I've said earlier with the copper example in my first part, I think a conductor has less resistance while an insulator will have more resistance. Now depending on which material you use, you're using lead, you're using wrought iron, you're using copper, that will greatly affect your resistance. You know, if you're trying to build a circuit and you have such things, you will have to consider which material you're using. Okay, and to our fourth and final affecting parameter, which would be temperature. Okay, we have temperature. Now temperature affects the value of the resistance because the capacity of resistance of the material increases as its temperature increases. So I would say it's directly proportional. So Let me just write it down for you so you can grab it here as temperature is generally the case. Okay. Okay, but most of the time it's such a small amount that it's negligible. But I will explore more on this chapter much more later on our module. So therefore now for a certain material at a certain temperature, our resistance R would be the length over area. Okay. Now we're going to do a lot of maths. Now we will consider the nature, or let me say the effect of the material through a constant of proportionality. I will introduce a constant of proportionality. Okay, we did not consider it in this first equation. Now considering it, then our formula would change. It would be R, our constant of proportionality, which is rho L over A. Okay, you can call this this is what governs the nature of the material. Now this will be different for copper, for wrought iron, for lead, for gold. You know, it will depend, or maybe carbon. It changes with material. Okay, or you can also call it the specific resistivity. Okay, its measurement would be, it will be measured in ohm meters. Okay, hope we can get that. Oh, sorry. Let's continue on this page. I don't want us to rush that much, so we'll go on to resistivity and conduction. All right, I hope we got the first part here of this formula, because we're gonna bring it back here to derive a few of our formulas. Now resistivity also depends on the nature of the material. Like I said, it would be rho. But how did we get to these units? Well, if I put it like this, make it the subject of the formula, which is R times A over length, which means that it's ohms multiplied by meters squared divided by meters. Now these two are going to cancel out. Well, one will be left, which means we got rho ohm. We got ohms, meters as our units. Now let's write down its definition so that we do not forget. Okay, the resistance of a material having a unit length and unit cross-sectional area is known as its specific resistivity. And let me just paste a table here of different kinds of material we would be dealing with now. So I've quickly jotted down a couple of materials that you would be very you should be very wary of, that we'll be using here, and also their values of resistivity. I've written down here on the side. This is in ohm meters. Okay, this is copper, this is aluminium cast, this is bronze, this is wrought iron, this is carbon graphite, it's gold, it's silver, and it's lead. Okay, I hope we can get that. Let us continue on with our chapter, and we'll do a couple of examples before we head on to our tutorials. Now, one thing to note here is that the material with the highest value of resistivity is the best insulator, while the one with the poorest value of resistivity is the best conductor. So here our best insulator, our best conductor would be copper, because it has the highest value of resistivity, and the one with the lowest value or the poorest value would be our best conductor. Okay, now let's go to conductance, right? Let's deal with conductance. For conductance is the inverse of what? Okay, firstly, how does it relate to the material? Well, conductance of a material is actually the reciprocal of its resistance, and we would denote it by G. Okay, by G. It's actually the reciprocal of resistance, not of resistivity. So we should be careful of that, of resistance, not of resistivity. So G, meaning that G would be 1 over R. Okay, now what does this actually mean? What is the actual definition of it? Now, it is actually the indication of ease with which the current can flow through the material, or the wire in this case. It is measured in Siemens. Okay, it is how easily the current can flow inside of a wire, and you would measure it in Siemens. Siemens. Okay, that's what I mean. Not okay. And how would I derive an equation for that? So okay, so G is equal to 1 over R, like I said, which is area over rho multiplied by L. That's R, in fact. So if you flip that over, you'd get this, and then you do a little bit of breaking apart. Now this right over here would form its own how can I say, its own parameter in this case. Okay, which I would call conductivity. This will introduce us to another conductivity, to another factor of resistance. I shall call it conductivity. Well, it's called conductivity. I'm not gonna call it conductivity. That's what it's actually called. Okay, now we should note that this quantity 1 over rho that I put up here, it's actually the conductivity. Okay, and it is denoted by this sigma, or let me just write it down here. It is sigma. Okay, now it's measured in Siemens per meter. Now, what we should also know about this one is that the material having the highest value of conductivity is the best conductor, while the one having the poorest conductivity is the best insulator. Okay, it's almost similar to what we had for resistivity. Okay, so let's go on with some examples. Let me play some examples here and let's hope for the best. All right. Okay, so now I've set up our first two examples here from chapter 1. The first one goes as follows. The resistance of a copper wire 25 meters long is found to be 50 ohms. If its diameter is 1 millimeter, calculate the resistivity of the copper. All right, let's not waste any time here. Let's begin. So always start with what you are given. In this case, we are given the length, 25 meters of it. We're given the diameter, which is 1 millimeter. We are given the resistance as 50 ohms. Okay, so this is pretty straightforward. What we need is the area before we can plug it inside our formula. Now the area of this cross section, because since we are given a diameter, we're going to assume it is a circle. So we will use this equation, d squared, which is equal to pi over 4, that 1 millimeter squared, which is going to give us 0.7853 square millimeters. Therefore, rho, which is equal to RA over L, since we are making it the subject of the formula, is equal to 50 multiplied by, okay, one thing we have to remember is that 1 millimeter is equal to 10 to the power of negative 3 meters. So if we want to convert this back into meters, we'll multiply by 10 to the power of negative 6, 0.78, 53 times 10 to the negative 6, all divided by this 25 meters, which is going to give us 1.57 times 10 to the negative 6 ohm meters. Okay, that one was pretty straightforward, I must say. Okay, let us continue with the second example, which is calculate the resistance of 100 meter length of wire having a uniform cross section area of 0.02 millimeters squared and having a resistivity of 40 microohms centimeters. All right, for 1.2, what we are given is a 100 meters of length, right? And we are given an area of 0.02 millimeters, I think. Yes, we are. And we are given a resistivity of 40 microohms centimeters. back to our usual formula, which is R rho L divided by the area, which is 40. Okay, now this is 40 micro ohm centimeters. What we need to do is we need to convert it into square meters, and rho needs to be in ohm meters. Okay, so what I'm going to do, I'm going to multiply this 40 by 10 to the negative 6 since it is micro, and I'll multiply this centimeter by 10 to the power of negative 2, 0.02, and then the area would be of negative 6, and the answer would be 2000 ohms. That was also a pretty straightforward example. And this one is a continuation of it. I've highlighted it in red because it's more likely to appear in your exams. It's quite a tricky question, but it's not that difficult. It's just the way they're asking it. If the wire is now drawn out to 4 times its original length, calculate its new resistance. Okay. Now the wire is drawn out such that, let's call it the new wire L dash will be equal to 4 times the original length of this wire. Okay. But now, how to continue? What stays constant once we assume this? It is the volume. The volume, you might draw out that wire, but the volume, it must remain constant. It must remain the same. Okay. Now, having that in mind, we will use that to our advantage. Okay. Now, what's the formula for volume? So volume for a cylindrical wire would be the area multiplied by its length. But in our case, we want the area dash multiplied by the length dash, since these are the new areas and the new lengths of our wire, right? So if we equate these two equations and make A dash our subject of the formula, we'll be left with A times L divided by L dash, which is equal to A multiplied by L divided by, what's L dash? I did say L dash is equal to 4L from first. Now these two L's, they are going to cancel each other out, and I'll be left with area divided by 4. Now let's say this R will be our new resistance. It will be equal to rho. Since rho won't change, it will remain as rho multiplied by L dash divided by A dash. These two have changed, right? Which is equal to rho. What's our L dash? Our L dash is 4L divided by, what's our A dash? It is A divided by 4. Now if I multiply this 4 with this 4, that will give me 16, and I'll be left with this P and then this L. This P and then this L, and then I'll be left with A here at the bottom. But we already know that this PL over A is going to give us what? This 2000, because that's the resistance. Okay, that was our original resistance. Therefore, we'll be left with 16 multiplied by 2000, which I think is 32, right? 16 times 32, 16 times 2000 would be, yes, it is actually 32,000 ohms. Okay, now let us see our next tutorial and see if you can try and attempt it. And now unfortunately I've run out of time for today, but as you can see, this is the tutorial that I've set up. So number one, it says a silver wire has a resistance of 2.5 ohms. What would be the resistance of a manganese wire having a diameter half of the silver wire and length 1/3? Now, and we are told that the specific resistance of manganese is 30 times that of silver. And I've written down the answer as 100 ohms. Now I've done the solution for this. I've already done it on the side, but if you want, if you've attempted it and got stuck, I can give you the breakdown of the solution. You just need to email me. I'll put my email on the description below. And I've highlighted the second tutorial red because it's most likely to appear in your exams. As I've said, this is quite a tricky one. It's quite difficult, you know, but it is quite doable, you know. It's quite doable, and I can give you the step-by-step solution. You just have to email me or like and comment if you'd like me to email you the solution for this. Or maybe if you like and comment on the video, I will maybe do a separate video on this tutorial at the end of this chapter. I'll go through it step by step on how to approach it, how you could use what we've done before to get these answers correctly. Okay, and I'll see you on the next chapter that we'll be covering, which is part 3 of our chapter 1, which is also on the effects of resistance on a circuit or on our current, you know. And I'll see you later, guys. Hope you have a nice day, and thank you.